Since the formation of our planet's oceans, sea levels have been rising and falling. It's a complex cycle caused by natural climate variations that occur over millions of years.
Talking about sea level changes in time, over the last 800,000 years, we've had at least 8 cycles in which sea level has gone up and down in the order of 300 to 400 feet, 110 to 120 meters. What we don't really understand is really what's driven it, and we don't really understand the rates in detail, and we don't understand what that means to the future.
Over the last 18,000 years, the Earth has been steadily warming and sea levels have been rising. But recently, this warming has been occurring much faster than ever before, and it's becoming critical to better understand the climatic processes that are affecting our oceans. Scientists rely on clues from the past in order to predict how sea levels might rise in the future. A team of scientists and explorers are now looking for these clues in the oceans around Bermuda.
Bermuda is an excellent tide gauge. We have lots of places other in the world where the land mass is moving up and down in response to mountain building, in response to sinking land masses. That complicates the issue. Here in Bermuda, we're dealing with simply the question of the sea level rise due to what's happening to the ocean.
Variations in climate cause changes in sea levels. When the Earth is cooler, sea levels are lower. When the Earth warms, sea levels rise, for 2 reasons. Melting ice from glaciers and polar ice caps returns more water to the oceans. More importantly, when water gets warmer, the oceans actually swell, causing sea levels to rise. We call this thermal expansion. However, while we know the general causes of sea level rise, we don't know exactly how fast this process has occurred in the past. Bermuda provides a perfect record of these changes, if you know where to look. And on Bermuda, no one knows where to look better than ocean explorer Teddy Tucker. Born and raised in Bermuda, Teddy's been diving and exploring the island's waters all his life.
Teddy and I have had a chance over the last few years to discuss his 50 years underwater. And in the meantime, I was also trying to understand the geologic history of Bermuda. He and I started to compare notes, and I was asking him, did he know of any evidence when sea levels were lower, and began to realize Teddy had made some rather interesting observations, one of which he had said that while investigating the area around Gurnet Rock, he was looking for shipwrecks, and he found wood on the bottom, and he thought that was part of a gunwale or part of a ship's structure, and he had went down to investigate, excavated, dug around, and found that it wasn't a wreck at all. It was a root system, and that there was soil around the root, and there was actually stumps present. So is that the kind of evidence you're looking for? And I said, that's exactly what we're looking for.
Aboard Teddy's boat, Steve is now on his way to explore this ancient mystery. He and Teddy are leading an expedition to investigate the stumps and find out exactly how old they are. To accomplish this, they'll have to dig one up from the sea floor. They've arrived at Gurnet Rock, and everyone is eager to find the stumps.
All out in here, all of this area here that you see sand was all the remnants of a prehistoric cedar forest.
Since cedars can't grow underwater, Steve knows that the area around Gurnet Rock must have been dry land at some point in the past.
The sea level rose, Gurnet Rock protected the area behind it from erosion and destruction, and we had the preservation of these tree stumps. So what we're doing now is trying to understand the distribution of stumps and map them out, determine their exact depth below sea surface, and then radiocarbon date them, determine the time at which they died.
So the question really here is, how old are these stumps? And the date that the stumps died is the date the sea level overtook them and killed them. Well, we got a perfect day for it. The water's clear, it's calm, it's sunny out, so we might as well get in the water and find these stumps.
All right.
The stumps don't actually look like much at first glance, just a spider web of roots in the sand. That's because they were worn smooth by wind and waves as the sea level rose over the forest. But after thousands of years, it's amazing that even the roots have survived. But how did the trees die? Some believe that the ancient cedar forest could have been destroyed by an asteroid.
The outer part of the tree shows evidence of burn all through the upper part of the root system. And there's two ways to interpret that. First is that as sea level rose and inundated the root system, it killed the tree. Tree died, was then subject, of course, to burning through lightning strikes, and the forest would have burned and left the charred remains. There's another explanation. Teddy believes that the tree was actually living at the time it burned. The trouble is, it's very difficult to burn a live cedar. And that means you need a very intense heat source. And the only explanation for that is possibly a meteorite.
An asteroid hitting or even passing nearby Bermuda would have caused a massive fire, burning the trees before they were flooded. But Steve and other scientists believe that the trees were killed by rising seas. That's the hypothesis behind this research expedition. After excavating the roots, Teddy has been able to get a rope underneath the stump in order to hoist it from the sea floor. Teddy powers the engine and the rope tightens. For a while, it appears that the stump won't budge. It's a dangerous situation because the rope is under so much tension, it could break before the stump gives way. The noise underwater grows to a loud roar as Teddy revs the engine higher and higher. At last, the stump is freed from the sea floor after thousands of years on the bottom. The disturbance has kicked up sediment, hampering visibility. But everyone is thrilled that the stump came up in one piece. With the stump loose on the bottom, the team hauls it up to the boat. After a successful collecting trip at Gurnet Rock, the team triumphantly returns to harbor, Cedar stump in tow. Steve collects samples of the stump to send to the lab for carbon dating to find out exactly how old the forest is. The wood is extremely hard, and even after so many thousand years, it still smells like cedar. But pulling up the stump is only the beginning of Steve's investigation into Bermuda's record of the world's rising and falling oceans. To get a clearer picture of Bermuda's past, Steve goes to Paget Marsh, a present-day cedar forest that may provide clues about the environment of the stumps.
Quite often in geology, use the present as the key to the past. We go back in time to a period when sea level was lower at Gurnet Rock by at least 10 meters, if not more. A forest such as this, a cedar forest, proliferated in the area and survived, was very healthy. The changes started to occur as sea level came up, and the root systems of those cedars were exposed to salt water. Taking a look at the case today, sea level is continuing to rise around the world, and we've had some high tides in the last couple of years. With that rise, we've had this area inundated with salt water for the very first time. And if we're right about what's going on in Gurnet Rock, it's quite possible that rising sea levels flooded that forest at that time, just like this forest now, and wiped out the cedar trees. So the question is, do we have a modern analog here for what happened several thousand years ago at Granite Rock.
Geologists know that warmer temperatures have caused sea levels to rise 350 feet in the last 18,000 years. Though we don't know when, at some point during this period, the rising water drowned the cedars at Granite Rock. Scientists use a graph to visualize changes in the ocean's depth over time. This is called a sea level rise curve. We begin by plotting today's sea level. We know that 18,000 years ago, at the peak of the last ice age, sea level was 350 feet below its current level because great amounts of ocean water had been converted to glacial ice. Though we know the total amount of rise, what is not as well understood is the rate of rise at any particular time during this period. By only looking at these 2 points, it's impossible to know exactly how sea level changed over time. It's possible that sea level has been rising at a constant rate, as this line suggests. It's also possible that sea level started rising slowly and sped up over time, as this curve suggests. Finally, it's also possible that sea level rose rapidly at first and then slowed down more recently. As you can see, while you can make a curve with only 2 points, it's impossible to know the correct shape.
You can define a curve with 2 points. But if you have 50 points, the curve becomes much more defined. So there's been an evolution, and as more and more data is collected, we get a much better idea of really what's happening.
The stump at Granite Rock is a great source of evidence, but Steve needs more data points to better refine the shape of the curve. Teddy is leading the team to Ferry Reach, where they hope to find more information about sea level rise. Teddy believes that the sea floor around this protected cove was once a freshwater lake that existed at about the same time as the Granite Rock forest.
It was definitely a freshwater lake, and I think this was the northern perimeter of it. What happens is the leaves and everything would have been washed down here by wind as it fell off the foliage in the water, and then just sunk here.
A preserved lake bed is extremely useful to Steve's climate research because it provides a record of what types of plants and animals lived at that time, and these organic remains can be dated just like the cedar stump at Granite Rock.
We take sediment samples of the seafloor, and then you can bring those up and examine and study the different layers with depth. And of course, the deeper you go, the further you go back in time. And we can actually reconstruct climates of the past by the presence of organic remains, such as, for example, tree leaves, little animal remains, pollen from trees and bushes. All of those are clear indications of what was growing and living in the past. We wrap it in aluminum foil, which is inert, and we then send it to a lab. We can then use those organic remains to get a quite accurate date and start to interpret the climate, whether it was hot, dry, warm, or wet.
Teddy's excavation of the seafloor at Ferry Reach revealed a 4-foot-thick layer of debris called peat, which is formed when organic material falls into a lake or swamp and is preserved on the bottom.
The story of the sea level history of Bermuda gets very interesting because now we have 2 quite different kinds of evidence. One is the drowned forest at Granite Rock, and the other is perhaps this evidence of a large lake that existed at Ferry Reach.
6 months later, Steve has returned to Bermuda for another expedition, and the carbon dates are back from the lab. The results confirm that at Ferry Reach, a freshwater lake must have existed. Throughout the life of the lake, peat was deposited on the bottom until the freshwater lake was eventually overtaken by the rising Atlantic Ocean. The bottom of the peat was dated at 5,810 years old, and the top was 4,920 years old. This means that a lake existed at this site for at least 890 years. But the real surprise was the date from the Granite Rock stump.
We actually were thinking that based on previous information and historic information that the tree is probably somewhere in the order of about 6,000 years old. And we received a phone call one day and they said, gee, this was a very nice sample, straightforward to date, no evidence of contamination, so we can get a very accurate date, and your tree is 7,290 years old, plus or minus 60 years. Not plus or minus 3,000 years, plus or minus 60 years. So we were quite excited. A, it was older than we thought, and B, that it was such a well-defined date. It might ultimately actually shift the curve. We might turn around and say, you know, the curve needs to accommodate this and needs to be shifted. Much like the previous investigators. When they added new data, the curve moved, and we'll probably do the same.
But to determine whether this data will really shift the curve, Steve needs to nail down the exact water depth at which the tree died. So he's returned to Bermuda with a sophisticated new sonar tool that can map the topography or shape of the seafloor around the stump.
In order for us to determine how sea level rose and the rate at which sea level is rising now, both in the past and for prediction for the future, we have to know the time and the depth. So in this case, we now have the time tied down 7,290 years ago, but we now clearly need to understand the depth that the stump is located at and the depth at which the stump actually died.
If the seafloor was consistently sloped around Gurnet Rock, then Steve could be confident that sea level was at the height of the cedar's roots exactly 7,290 years ago. Steve needs to precisely determine the exact depth of the ocean when the tree died, because a different depth could actually move the sea level rise curve.
So it's important for us to go back to Gurnet Rock and clearly understand the topography of the seabed, to understand how water actually reached the root system and killed the tree.
The team has brought a multi-beam mapping system that consists of 3 basic components: a sonar unit which measures how deep the water is around the boat, a GPS or global positioning system receiver which displays exactly where the boat is, and the computers which collect all the data. Battery power is critical to keep the system running.
One battery is 12.39 and the other is reading 12.73, so not too bad.
Okay, you all ready to fire it up? Okay, let's go.
With the system up and running, Bob Harms, the multi-beam specialist, begins collecting data.
Okay, we have the same lines we ran from the last survey, Teddy.
What we do with sound to look at the seabed is the same as you would do with an aerial photograph, taking pictures from an airplane looking down. We're looking down, only we're using sound instead of a photograph. This is the display of the signal that we're getting from the multi-beam transducer that's being towed off the stern of the boat. So it shows the pattern of the seabed as we move along. The transducer sends out a sound wave, or in this case 6 beams of sound, and they bounce off the seabed, and the transducer picks up the sound and transmits it to this display and to the computer.
Just as planes or satellites have to fly over the area they want to photograph, Teddy has to pilot the boat over the areas of the seafloor that Steve wants to map. He drives a pattern back and forth like a lawnmower, covering a bit more of the seafloor with each pass. It's a long day on the water. The system must be carefully monitored to make sure the soundings are accurate and that there are no gaps in the coverage of the bottom.
Basically, it's just a bunch of numbers that are being captured in files at this point. When we get back home, we're going to process those numbers into imagery. We set up a few little programs to strip out the actual geographic coordinates, the XY coordinates of where we are in the world, and relate that to the depth sounding that we're getting from the instruments, so that we know at any particular spot where we're surveying, we know where we are and how deep it is.
What do you think, Bob? We got enough coverage to say we kind of got a pretty good data coverage for Turner?
I think so. I think there'd be enough there to produce a mosaic of the areas, the 3 areas that we've done so far. So,
what about the line spacing in here?
It's not bad. We could have filled in a few more lines, but no, I think that'll be just fine.
The data gathered on this expedition has been transformed into a topographic map of the seafloor around Gurnet Rock. The different colors represent elevation changes in the seafloor, The deepest areas are blue and the shallowest are red. The 3D map gives Steve more precise information about how the stump was flooded. In the past, when sea levels were lower, the red, yellow, and green areas would have been dry land. This is when the cedar forest lived around Gurnet Rock. You can see how rising waters would have suddenly flooded the green areas, submerging the cedar forest. Over the years, sea level has continued to rise so that today, only Gurnet Rock remains exposed. The research in Bermuda is providing new data that will help improve sea level rise predictions for the future.
It's becoming more evident in the last 10 years that clearly understanding and defining a very accurate curve is important for our future. Everywhere in the world today, we're starting to see the effects of climate change and sea levels rising.
There is now little doubt that human activities like burning fossil fuels to power our cars and produce electricity have been causing our climate to warm at an accelerated rate over the last 100 years. Over the next 100 years, many scientists predict that sea level will rise by at least 1.5 feet. Though it doesn't sound like much, even a 1-foot rise in sea level would be devastating, bringing increased storm damage and erosion to vulnerable coastal communities around the world, including Bermuda. In September of 2003, Hurricane Fabian collided with Bermuda, causing hundreds of millions of dollars in damages. Not only did the storm damage buildings and roads, but Hurricane Fabian also completely reformed part of the Bermuda coastline.
As scientists, we really need to make sure we clearly know what's really happening with sea level, at what rate our coastlines are being exposed to rising sea levels, and what rate they're going to be damaged. We can then design for it, we can engineer for it in terms of the buildings, the structures, everything from residences to cottages to businesses to harbors. We mostly live on the coast. So it affects us all across society, right from a recreational standpoint, commercial, and our economy, and it's major.
Today, the Earth's climate is already being altered by human activities. But how much more will natural influences add to these effects? By carefully studying what happened here in Bermuda 7,000 years ago, Steve and Teddy's research is helping to differentiate natural sea level rise from human influences. It is this kind of science that will help us all learn to cope with the inevitable changes that affect all life on Earth.